In the dense forests of Central and South America lives the most formidable predator of the sky. Swooping in between the branches of the canopy, snatching its prey from above and below, the harpy eagle is a terrifyingly agile predator. It hunts by sight and hearing, carefully scanning the canopy for prey, which it can spot from huge distances. It has a grip strong enough to crush its prey's bones in an instant, and can lift prey that weighs as much as its own body weight. Among the largest of the eagles, a harpy eagle's wingspan can reach to up to over 2 meters. Wings perfectly suited to maneuvering in the dense forest vegetation. They can weigh up to 10 kilograms or over 20 pounds, yet can still fly at speeds up to 80 kilometers per hour, packing a huge punch on impact for their unfortunate victims. In one incident, a harpy eagle even nearly knocked a BBC cameraman unconscious, and could have killed him if it weren't for the man's stab-proof Kevlar vest. These eagles are arguably the most powerful of all of the raptors. Being a sloth or a monkey in harpy eagle territory would be an unfortunate fate. But it's not just raw power that makes the harpy eagle one of the deadliest predators of the rainforest. These eagles are also incredibly intelligent. So intelligent that their smarts rival that of their primate prey. The relationship between the eagles and the monkeys that they hunt has evolved into an extraordinary arms race of cleverness, each pushing the other to adapt new communication, defenses, and attack strategies over time. With legendary strength and fearsome hunting abilities, the harpy eagle is a force unmatched in the sky. How has nature crafted the harpy eagle to be such a monstrous predator? What is it that makes the harpy eagle the scariest killer of the sky? The first written record of the harpy eagle is in Carl Linnaeus' 1758 Systema Naturae. He describes the bird as the vulture harpia, named after the Greek mythological spirit, the harpy, that had the body of an eagle and the face of a human. This comparison is fitting, largely due to the harpy eagle's facial disc. The facial disc is composed of feathers that form a circle around the bird's face, which they can lift or lower as they please. When the feathers of the facial disc are raised, they help direct sounds to the bird's ears, which are located on the sides of its head. It's a lot like when you cup your hands behind your ears to hear something better. This allows the eagles to pinpoint prey in the dark, dense forest where it hunts. Harpies will often perch completely still and completely silently as it waits for prey to wander near them. And to help in spotting their prey, harpy eagles have some of the best eyesight of any animal in the world. They can spot an item as small as 3 centimeters from 200 meters away. This level of acuity, the ability to resolve fine detail in their eyes, far exceeds our own. To test just how well eagles can see, researchers set up a clever experiment. They trained eagles to fly down a long tunnel towards 2 TV screens. One TV would display a striped pattern, and when the birds land on it, they get rewarded with food. The other TV displays a solid gray color. The TVs were then separated, so the eagle had to make a choice at the start of the trial and stick to it. Over the course of the trials, researchers would determine from what distance the eagles can discern the stripes and choose the correct TV. The eagles were found to be able to discriminate detail that is 4 times as fine as the finest detail that we can see. A few features of an eagle's eyes make them so sharp. For one thing, eagles have large eyes for their size, 1.4 times greater than the average for other birds of the same weight. And the eye is tube-shaped. The tube shape produces a larger retinal image. And this retinal image is transformed into a neural response by the light-sensitive elements of the eye, the photoreceptors. The more photoreceptors there are, and the less space between them, the better the visual acuity. As the spacing between photoreceptors decreases, so does the minimum size of the detail that can be discriminated by an eye. However, simply having more photoreceptors spread all over the retina would be energetically costly. Because of this, animal eyes have a special central region with extremely numerous and tightly packed photoreceptors. This is called the fovea, and it provides the brain with the clearest vision of any part of the eye. Eagles have a much deeper fovea than most animals, giving them especially high acuity vision. For harpy eagles, the highest acuity occurs in their peripheral vision, at around 45 degrees to the right and left of their head axis, and it's usually used for detecting prey from a large distance. But pursuit raptors like the harpy eagle have something else almost no other animal has. A second, shallower fovea that allows for sharp vision in the frontal field of view, at 15 degrees to the right or left of the head axis. These 2 foveae allow the eagles to see 2 sharp images in their vision simultaneously. This is why you can often see raptors like this, turning their head repeatedly while looking at an object. They can't rotate their eyes in their sockets, so these movements are helping to focus the object back and forth between the deep and shallow fovea. Having both regions of acute vision is, of course, a huge benefit to these predatory birds. But having their most acute vision in the side of their vision causes a conflict for many raptors, especially ones that dive at prey at high speeds. When going fast, turning the head sideways to view the prey that's in front of them would cause a ton of aerodynamic drag and slow the bird down. So to solve this, raptors don't necessarily follow a straight path to their prey. Instead, they dive along a logarithmic spiral path with their heads straight and one eye looking sideways at the prey. This is especially true for birds like the diving peregrine falcons. Harpy eagles don't fly or dive nearly as fast, but at 80 kilometers per hour, they still very much need to keep aerodynamics in mind as they hunt. From wingtip to wingtip, harpy eagles are longer than many full-grown humans are tall, with a wingspan of about 2 meters across, with female harpies being almost twice the size as males. These wings are immense, but for the size of the rest of their body, and compared to other large flying birds, their wings are relatively short. Andean condors, for example, weigh about the same as harpy eagles, but have a wingspan of over 3 meters across. This is because harpy eagles aren't built for soaring. Instead, they're built to move more nimbly from tree to tree through the dense forest. Their short, broad wings help them be highly agile, and even give them the ability to fly almost straight up, so they can attack prey from below as well as above. Like with all flying birds, harpy eagles are able to fly due to the structure of their flight feathers, or remiges. Unlike other feathers, remiges are anchored to the bone, and their primary function is to aid in the generation of both thrust and lift. Remiges are divided into primary and secondary feathers based on their position along the wing. The primaries are the longest of the flight feathers. These feathers are asymmetric with a shorter, less flexible leading edge that prevents mid-air twisting. They occupy the outer half of the wing and can be controlled and rotated individually, much like our own fingers. This rotation of the feathers controls flight directions and adjusts lift and air resistance as needed. For example, if the primary feathers are lifted and splayed, the bird's flight will slow and the altitude will drop. If the primary feathers are held tightly together, the bird's flight will be faster and more precise, and is often done when chasing prey. This ability to morph the wing in different flying situations gives flying birds a maneuverability that aircraft engineers could only dream of. Secondary flight feathers cannot be controlled as extensively, but they provide most of the lift by overlapping to form an efficient airfoil. Tail feathers, or rectrices, are also essential for flight. They are needed for steering, and only the 2 most central feathers attach to the bone. Where the harpy eagle lacks length and wingspan, it makes up for in its long tail, which it uses like a rudder on a boat to steer through dense vegetation. Tail feathers are more symmetrical than flight feathers, but have increasing levels of asymmetry towards the outer pairs. And controlling most of this acrobatic flight are the chest muscles, which attach to the sternum. The chest muscles and sternum are highly developed in birds, much more so than in other vertebrates like mammals. But for the harpy eagle, it's even more extreme. Soaring birds like the Andean condor have a comparatively small sternum and less developed chest muscles. Once birds like them are airborne, they hardly need to flap. But harpy eagles, with their short wings and heavy weight and agile lifestyle, have a huge need for some of the strongest flight muscles of any bird. And on top of this strength, the harpy eagle's legs can be as thick as a human wrist. And its curved black talons are larger than a grizzly bear's claws, at 13 centimeters long. These are the largest talons of any bird of prey, and can exert over 50 kilograms of pressure. These claws are known to break bones in an instant, or snatch prey from trees with a force stronger than a large dog's jaws. This fierce hunting ability alone would be enough to strike terror in the hearts of the primates and sloths of South America. But on top of this, harpy eagles are clever. So clever that they don't merely ambush their prey, but outsmart them, in one of the most interesting predator-prey communication arms races ever observed. In the battle of survival in the animal kingdom, predators need to capture prey, and prey needs to avoid being captured. These simple truths have led to a spectacular phenomenon. Predators and prey throughout the world are locked in all sorts of evolutionary arms races. One famous example of this is the arms race between bats and moths. This arms race began when bats evolved the ability to echolocate, in order to detect their moth prey in complete darkness. In response, moths evolved ears that allow them to hear the echolocation and evade capture. Some bats then improved their attack strategy by evolving stealthier echolocation. That is, echolocation at frequencies that can't be heard by moths. Some moths, in turn, then evolved ultrasonic clicks of their own that they can use defensively during an attack. And so it goes on and on. These types of dynamics can be seen throughout the animal kingdom. But for a long time, relatively little was known about how predators hunt primates in particular, and how primates might acquire adaptive responses to counteract such predation. So researchers began a somewhat brutal observational experiment. Barro Colorado Island is a biological reserve island in the middle of the Panama Canal. It's home to many species of primate, including marmosets, spider monkeys, and most importantly to this study, howler monkeys. These howler monkeys lived in approximately 65 troops, each with an average of 19 members. Often, primates develop predator-specific calls that discriminate between big cats, snakes, and eagles, to warn their fellow monkeys of the specific type of danger that is near, and coordinate a defensive response. But for the last 100 years, the howler monkeys on Barro Colorado Island have faced no major predators. No jaguars, few snakes, and most importantly, no eagles. That is, until 1999, when 2 radio-collared harpy eagles were introduced. Researchers wanted to know, would the Barro Colorado monkeys have an organized reaction to the never-before-seen predators? And if they didn't, how long would it take for such a response to develop? As expected, once the eagles were set loose, they wreaked havoc on the monkeys. Both eagles were picking a howler monkey off every 3 to 4 days. And at first, the monkeys had one of 2 responses to a harpy eagle attack. Either they would act in a random, panicked and agitated manner with no coordination between the monkeys, or they would remain totally calm, completely unaware of the danger before them. The howler monkeys had indeed lost their ability to recognize the danger from the harpy eagle, thus becoming extremely vulnerable to predation upon their reintroduction. This is not altogether that surprising. The surprising finding, however, was the strategy the eagles used to hunt their primate prey. Instead of rapid stealth attacks, like you might expect, the eagles would perch in a tree nearby, in plain view of the monkey troop, and observe the animals. Then, as if to make their presence known, they would utter a series of calls, literally the opposite of stealth. These calls always had the same acoustic structure, were only ever used before prey pursuit, and only when hunting for primate prey. Why would a predator let its prey know that it's about to attack them? What happened after the harpy's call gave researchers a hint. If after the harpy made its presence known with its call, and the howler monkey's response was either minimal or chaotic, the eagles would attack. If instead, the monkeys displayed a coordinated defense response, the harpies would leave, and either find different monkeys to prey upon, or come back later and attack using stealth. The harpy eagle's call was being used to gain critical information about its prey. By observing what happens after the call, the eagles are learning about the level of prey alertness, their escape ability, and their defense mechanisms. By probing the potential defense strategies before initiating an attack, the eagle can assess the risk of the confrontation and make a snap decision whether or not it's a good use of their time and energy. Over time, more and more of the monkey troops established coordinated defenses, such as picking up the young and moving them closer to the trunk of the tree, moving to more dense areas of the canopy, organizing themselves to literally mob the eagle if it came too close, or producing an eagle-specific alarm call. After just a year, nearly all of the monkeys on the island had regained such defense mechanisms, making hunting for the harpies more difficult. Researchers got to observe this predator-prey arms race play out in real time, a unique and valuable opportunity. But unfortunately for our curiosity, the experiment ended before the eagles could adapt once more to the monkeys' new defense strategies. The harpies were removed from the island after just 1 year. But after they were gone, the howler monkeys maintained their defense responses to recordings of the harpy eagle calls for at least 7 months, which is how long they were observed for. No one knows for sure how long this defense response will last in the howler monkey population there. Field biology of this sort, unfortunately, can rarely continue on forever. But luckily, an incredible new insight into harpy eagle behavior was uncovered, proving in one more way that harpy eagles are an incredible predator.